Hi, everybody. Sorry for this technical difficulty on my part. But thanks a lot, Miguel, for the introduction and every organizer for the kind invitation. So this talk is about using anomalies as a tool to investigate the big question of string universality. Of course, since I can't see anybody, please interrupt me at any moment. But okay, so in the meantime, I will begin. So if I had to summarize this talk in a single sentence, I would say that it's about two interrelated but logically separate questions, namely, is string theory consistent? And is everything else inconsistent? Right? So these are the two main aspects of what people have come to call string universality, or also known as the string lamppost principle, right? The idea that string theory is the only consistent UV completion of gravity. And these two interrelated but different questions can be investigated with complementary approaches, right? So on the white side of this diagram calls more for a top-down sort of approach, namely, actually investigating whether concrete string theory constructions are consistent. Whereas the other side of the coin is more efficiently investigated in more of a bottom-up way by looking at large classes of bottom-up models. And this is the content of these two papers that I would like to talk about today. So this one here on the right, which came out a bit earlier, I wrote together with Aaron de Bray, Matilda Delgado, and Miguel Montero, whereas the other one deals with more bottom-up setup, namely supergravity theories in 6 dimensions, which I wrote with Giorgio Leone from Torino. And also I would like to point out that both Matilda and Giorgio are really good PhD students who are applying for postdocs now. So you may want to keep that in mind. Good. So this is the central question of what I'm going to talk about. And so let's begin with a brief lightning review of string universality, right? So string universality, again, is this idea that string theory is the only possible UV completion of gravity, or perhaps one can go to a priori weaker version of the statement, namely that every consistent EFT of gravity has a UV completion that is stringy, right? A priori, this wouldn't exclude other completions, which is why it's useful to study both aspects of the story, the top-down and the bottom-up aspects of the story. We want to know whether everything else is inconsistent as well. So this question seems extremely daunting at first, right? I mean, how can we possibly study all possible EFTs and their UV completions and understand whether they're either stringy or they're inconsistent? I mean, it's really difficult in principle to tell. There's no rule and there's no recipe to conclusively determine whether some EFT actually does arise from string theory. We just didn't know about it. And in fact, new discoveries about the string landscape are being found, constantly, even very recently. And in fact, string universality was a prominent topic in the recent Paris workshop, affectionately dubbed Landscapia, the complementary one to Swamplandia. And there it was emphasized in a few talks that in fact the barely low energy massless degrees of freedom and their physics is not enough to fully determine the consistency of the theory. Understanding the higher lying states and their dynamics is also important, and it's very much non-trivial. Here I am going to talk about string universality in restricting purely to the massless degrees of freedom, in particular the chiral degrees of freedom that contribute to the usual anomalies that I'm going to use. And in this context, even with these restrictions, the story is very rich. And it's supposedly summarized in this table, which is surely incomplete, and this list of references, which is surely incomplete. I did try my best to, do justice to all the remarkable works that have been done in this direction over the years. But the main guiding principle here on how to proceed is to organize this task by degree of ease, namely by the number of supercharges of our EFTs, right? And in particular, there's, the maximal case of 32 supercharges is essentially understood. Everything arises as either, M theory or type 2 or toroidal compactifications thereof. But already at the level of 16 supercharges, things become quite interesting. Already at the level of 10-dimensional supergravity theories, the story is non-trivial. There are, in fact, EFTs that do not arise from type 1 or heterotic strings in 10 dimensions that naively one would have thought are consistent, but in fact they are not, for very subtle reasons related to how anomalies work. And then the story keeps getting richer and richer by going down. In this case, going down in dimensions. There is an extremely beautiful and rich story that is related to a combination of various considerations, I-folds, anomaly inflow, cobordism classes, and so on, that essentially, I would say, maybe not completely settles the issue, but almost. And once more, string universality seems to hold in these cases. Then, other than that, things, going down in dimensions and or supercharges, things start to get sparser and sparser. So the results are less comprehensive, but there are bounds. In particular, at the level of 6D minimal supergravities, there are many, many constraints coming from anomalies, anomaly inflow, and other considerations that, for example, provide finite landscapes in certain subsets of theories. For instance, theories with sufficiently small numbers of hypermultiplets and non-abelian gauge groups, right? There are still some pesky outliers that we would like to get rid of. For example, some infinite families of theories with unbounded abelian charges, and this I will deal with by the end of the talk. So the bottom line here is that the results are incredible as far as this is my point of view. I wouldn't have expected such sharp and comprehensive results. But the boundary is more or less here at the level of 60 minimal supergravities and in going below 8 superchargers, right? Perhaps even down to 0 superchargers. So the obvious directions to push the envelope are going down in supercharges, perhaps by keeping the maximal number of dimensions as 10 in such a way that anomalies are still quite constrained, and understanding more this boundary case of 6D and equal 1 supergravities, right? And the tool that I'm using in both cases is the tool of this more general type of anomalies called Difrid anomalies that have to do with the topology change, as I will explain. So this is the idea. These two papers are sort of connected by this overarching idea of pushing the envelope of string universality. Good. So the main tool, as I just said, is Difrid anomalies. So I'm going to introduce what they are. So in order to introduce them as efficiently as possible, I'm just going to introduce anomalies, or at least this particular type of anomalies, in a more modern language directly, right? Which connects with the very nice story that was developed in the 80s. So in the context I'm talking about, an anomaly is just the lack of invariance of some physical quantity, let's say a partition function, as a function of background gauge fields. So how can this variation be captured? I mean, in principle, it would look like one would have to compute the whole thing, and for interacting supergravity theories, it's very complicated to do it, even at the semi-classical level. But luckily, there is a very powerful tool which was developed by Diane Fried, and the idea is that to find the dependence on gauge field transformations of this partition function, we don't actually need to compute the whole thing, because there is an equivalent way, there's an equivalent phase that captures this variation, which is encoded in a topological field theory in one dimension higher. This is called the anomaly theory, this A of y. And so it was found that there is often, for instance, for Lagrangian theories, there is a concrete recipe to compute this thing. And this thing encodes the anomalies of the original physical theory. And it does so by extending space-time, I'm calling it X here, into a higher dimensional manifold Y, in such a way that X is the boundary Y. And then the gauge variation of this topological field theory matches the one of the partition function. So we only actually need to compute this anomaly theory here. Now it would seem naively that I just canceled all anomalies in all theories, but in reality, I just moved the issue into this dependence on this unphysical extension of space-time, right? So the result has to be independent of this extension. And so what I can do is I can take the difference of two such extensions, and what I get is essentially a glued together closed d+1 dimensional manifold, often called the bulk. And what I get is the condition that this anomaly theory has to vanish, namely has to be an integer, the phase has to be trivial for closed manifolds Y. And when these closed manifolds Y, which are now everything I'm going to talk about, are boundaries of a d+2 dimensional manifold Z, the anomaly actually turns out to reproduce the original perturbative or local anomaly, which is captured by the anomaly polynomial. So this story connects very nicely with the usual framework of anomaly polynomials and characteristic classes. So this is the framework, really nice framework, really convenient and powerful, but so far, mostly, at least until recently, it was not emphasized very much that the type of closed manifolds Y that have to be used, right? So far, the main characters in this story were manifolds built by taking spacetime and extending it into a sort of torus by closing a cylinder into itself up to a gauge transformation. So what this does is it produces what we needed, namely a closed loop in the space of gauge fields, but it does not touch the topology of spacetime itself. The idea is that if we want to include non-perturbative quantum gravity effects of topology change, we actually need to consider closed manifolds Y in which the topology of the space-time slice does change, and so we are not we are left with a stronger condition for anomaly cancellation, namely that the anomaly theory be trivial not just for these mapping tori, but for all closed manifolds. And these are the so-called Dye-Fried anomalies. And it has been shown in this very nice paper that, in fact, sometimes they produce strictly stronger constraints on EFTs. Right. So this is a depiction of what I'm trying to convey here. So this is a mapping torus, namely this disk is space-time, and then there's a cylinder, and along the cylinder there's a gauge transformation, and the two boundaries are glued into a torus. And in a more general setting, the topology of space-time can change, right? And again, this can produce more general constraints. So this is the setting. So now the task is reasonably clear, right? We just take our theory under consideration, and we just compute this anomaly on all possible closed manifolds. This seems pretty crazy and impossible to do, but fortunately, if the perturbative or local part of the anomaly cancels, the problem simplifies a lot. Namely, it turns out that this anomaly theory becomes invariant under cobordisms. The idea is that the difference between the anomaly theory evaluated on two closed manifolds Y that are cobordant, that can be deformed into each other by a cobordism, becomes the local anomaly of the cobordism itself, which again vanishes by assumption, right? So the task is now to determine which Bourdism group and classes determine the anomaly, and then one reduces in principle the problem to a finite number of calculations, right? So this is the idea. The idea is that the anomaly is invariant under the deformation of the manifold, let's say from M to N, which is done essentially by a sequence of surgeries which composes a higher dimensional manifold. And this process of deformation induces an equivalence relation, the relation of being cobordant. And the equivalence classes yield an abelian group, and at least for the cases we're interested in, we can usually find a finite number of generators. And so in practice, we only need to evaluate the anomaly on a finite number of manifolds. This is the idea. The actual important task, at least at the level of physics, is to determine what is the actual Bourdism relation to impose, right? What are the allowed deformations? What is the structure that needs to be preserved by these deformations? And in ordinary cases, one has to deal with perhaps spin structures or gauge bundles and stuff like that, orientation. But in the theories at stake here, turns out that there is a more complicated structure that needs to be imposed. And this turns out to be the MVP of the story. Okay, so quick recap on anomalies. Again, they capture the gauge variation of our physical theory, and we want them to vanish. Okay, they would signal inconsistencies of the theory. And they are encoded in this nice topological field theory. And this a priori stronger condition for cancellation, the condition of Difrid anomaly cancellation, amounts to imposing or requiring that this phase be trivial for all closed manifolds Y in D+1 dimensions, right? So basically, all the information of the physical theory is now distilled into the anomaly theory and the structure that these manifolds need to have. Everything else is irrelevant for these kinds of anomalies, at least. Okay? Good. So if there are no questions, I can move on to actually applying this tool to the two settings that I described in the beginning, namely the top-down setting of 10-dimensional non-supersymmetric strings and the more bottom-up counterpart of 6D supergravity theories. All right. So let's start with the 10D story. So in 10 dimensions, if we require the absence of tachyons at least, there's only a handful of string theories available. Out of the well-known 5 supersymmetric ones, type 2b has a very rich and beautiful story related to the cancellation of Difrid anomalies, which was discussed in detail in this paper, also in relation with other things related to the cobordism conjecture. As for the other chiral theories, all of them require the Green-Schwarz mechanism to cancel their anomalies. And turns out that this is the same story that happens in the non-supersymmetric counterparts that I'm looking at. So the non-supersymmetric theories in 10 dimensions that I'm looking at are these heterotic model here and these two orientifold models, right? And these three theories, as string theories, are very different. But at the level of anomaly cancellation, they share a lot of common features. And the first one being the Green-Schwarz mechanism. So how does this work? So both for all of these theories, type 1 heterotic and the non-SUSY ones, the basic mechanism that grants anomaly cancellation, at least at the level of local anomaly, is the fact that this, although the anomaly polynomial does not vanish, its irreducible piece vanishes. So the anomaly polynomial as a 10 plus 2, 12 form factorizes into a product of this type. And in the type 0 prime B theory, actually, the factorization is a bit more complicated. But the point is that the factorized form allows the total gauge variation of the partition function to be compensated by another piece. And this piece comes from an additional anomalous variation that comes from the B field or the curvature, the H field. Now, this H field can be either a Ramond-Ramond or an SNS field, depends on the theory, but I'm using the same notation for both. The point is that this H field has an anomalous Bianchi identity. And this brings along an anomalous gauge variation that exactly compensates the one induced by this anomaly polynomial here. So this is a remarkable property of these chiral string theories. And it turns out that a very similar mechanism happens in 6-dimensional supergravity theories. This time, it's a bit more complicated because there can be multiple H fields, just like in the type 0 prime B theory, there's 3 H fields of different degrees.
Can I ask you something before you go on?
Yes.
Let's understand, is this already the result from the non-SUSY? So you're saying that all anomalies get cancelled if you take into account the Green-Schwarz mechanism, and that's it?
So I'm saying that it was already known that the local anomaly cancels for non-SUSY theories because of the Green-Schwarz mechanism, yes.
But you're not saying that, yeah, so that's then all the cobordism groups vanish and you only
I'm
have
not
to
saying that yet. I'm saying that the purely perturbative anomaly cancels in these theories. And this was known since their inception.
Okay.
I just have a quick additional question on this. So you say you're talking about non-SUSY string theories without tachyons, but
yes,
you can talk about the ones with tachyons and then do the tachyon condensation to some sort of lower dimensional theory, but with some linear dilaton profile. Has it been checked that, like, for example, like local anomalies cancel?
I think so. I think that at least local anomaly cancellation has been checked. Moreover, at least for heterotic theories, perturbative heterotic theories, it always does because it follows from modular invariance in the end. In full generality, I'm not sure that Difrid anomaly cancel. I don't think it has been checked, and in fact, this would be a very interesting follow-up of this work. Because indeed, the lore is that, in principle, there's nothing wrong with tachyons, right? I mean, even if you cannot deal with the tachyon dynamically, as in perform the condensation explicitly, etc., the anomaly is supposed to be robust under these kinds of things. So I believe that it's plausible if we were to compute these kinds of anomalies I'm going to talk about in the tachyonic theories, they should vanish as well.
But one question with that related to like the computation of the cobordism. If you wanted to do that in that case, usually when you compute the cobordism classes, you do for a fixed dimension. In this case, as Ethan was saying, would you have to compute them for like the 10D theory with the tachyon or the lower dimension after the tachyon condensates?
This is a very good point. So let's say the following. So let's say you start in 10D, then the relevant cobordism group for anomalies in 10 dimensions is 11-dimensional boardism, as I explained before. Now, if such anomalies cancel, then all smooth compactifications of that theory are also free of anomalies, right? What happens if the compactification is not smooth? Perhaps it's even non-geometric, right? What happens then? The answer is I don't know. And in principle, a priori it needs to be checked independently. And in fact, I have an example of this at the end. Some cases can be excluded, without going about this process. This was done by Tashikawa recently for supersymmetric heterotic strings. It has been shown that all global anomalies for all possible lower dimensional theories, smooth or non-smooth compactifications of 10D theories, etc., all vanish. So sometimes in very lucky circumstances, things anomalies can be shown to vanish independently of whether the compactification is smooth. As for boardism, I think a priori it only guarantees that the lower dimensional theories are anomaly-free if the compactification is smooth. Otherwise, one needs to compute things independently in the lower dimensional theory.
Thanks.
Good. Thanks for the really nice questions. Good. So, as I was saying, this Green-Schwarz mechanism, which applies in these 10D non-SUSY strings to cancel the local anomaly, also applies in 6D supergravity, at least when the supergravity is consistent. And in this case, all the H fields are 3 forms, but there can be many of them because they can arise from tensor multiplets. And moreover, in 6 dimensions, they are self-dual. So they also contribute to the local anomaly themselves. So things are a bit more messy, and the anomalous Bianchi identities are always going to take this schematic form that the coefficients of the Pontryagin and Chern terms can be very different, right? In the 10D case, there's only one Bianchi identity and it's always the same. So in the 6D story, these constraints are very powerful, but as I mentioned in the beginning, the resulting landscape is still quite large. So then one can further impose the cancellation of the, let's say, ordinary global anomalies. And indeed, there are further constraints that appear. For instance, there are some constraints on the number of chiral, number of hypermultiplets in certain representations of certain groups, like this one. And then there are the powerful constraints coming from the unitarity of BPS strings via anomaly inflow, which also provides some bounds on ranks of gauge groups and the like. But once more, even accounting for all of this, the landscape, the putative landscape, let's say, remains quite large. So this is the story as for local anomalies are concerned. Bottom line, the Green-Schwarz mechanism is the main player. And you can see that the Green-Schwarz mechanism tells us that something has to happen in the topology of these backgrounds. There is a certain cohomology class that needs to be trivial, right? Some differential form is exact. This is the seed of the additional structure I was talking about. It's not, we cannot just say that spacetime is a spin manifold with some gauge bundle. Has to satisfy this particular anomalous Bianchi identity. And at the level still of local anomalies, all of this Green-Schwarz mechanism is encoded, as I said before, in an additional contribution to the anomaly theory. It's not just the ones coming from the chiral fields. there's also this additional piece coming from the anomalous variation ascribed to the H field, right? Because of the factorization of the anomaly polynomial, the local anomaly that comes from this guy cancels the local anomaly coming from the chiral fields. Now, what happens at the level of global anomalies? Well, at the level of global anomalies, cohomology classes that show up in these manifolds can often be torsional. They cannot be encoded just in differential forms. So there are other ways of writing down proper partition functions for fields that have torsional data. But the bottom line is that naively, a lot of theories would just be thrown out the window, including some string theories, because of anomalies on these manifolds that have torsional classes. But what saves the day is that die-free anomaly cancellation on the worksheet of strings propagating in these backgrounds actually tells us that the identity that I was telling you about before, the anomalous Bianchi identity, actually has to hold on a stronger level, at the level of integral cohomology. Namely, not only the differential form part needs to vanish, it needs to be exact at least, but the torsional part has to vanish as well. So this is the true protagonist of the story. The manifolds on which anomalies can be evaluated, the allowed backgrounds of these series, are what are called twisted string manifolds. So they are spin manifolds with some gauge bundle and a trivialization of this particular cohomology class. So that's the idea. These coefficients, once more, depend on theory, but the resulting Bordism groups are extremely unwieldy in principle, right? It's very difficult to compute them. So oftentimes the twisted string structure is just ignored, right? The ordinary spin Bordism is computed instead, and then one can sort of reverse engineer the allowed backgrounds from there. But the proper recipe ought to be to compute the actual twisted string Bordism and then compute the anomaly on that, right? So these are the allowed structures here. So let's just quickly recap once more, and then I will go to the actual meat of the work. So the tool we're using is these die-free anomalies, and the manifolds on which we look at these anomalies are twisted string manifolds. They have this twisted string structure. Now we apply this tool to study the consistency of these two top-down and bottom-up complementary settings, right? 10D non-SUSY strings and 6D supergravity. And while these the anomalies in these theories share lots of common features, there are lots of differences at the level of what we actually do. Most prominently, the top-down setting has just 3 theories to look at least the tachyon-free ones. So it is in fact feasible to do the full, to perform the full computation of Bordism groups, and then look systematically at the anomalies. In the case of 6D supergravity, it would take much longer time to do it because, at least a priori, the twisted string conditions are different. There are many twisted string structures to impose, depending on the particular theory. And so our strategy in this other work was rather not to compute the Bordism groups, but to compute some sample anomalies. Anomalies whose cancellation doesn't necessarily imply that the full theory is fully anomaly-free, but at least it's an indication. And finding a violation of anomaly cancellation for those cases would imply that the theory is anomalous. Then there's also an additional complication for 6D, which comes from self-dual tensor fields. And in this case, they also contribute to the anomaly in a way that is encoded by objects called quadratic refinements. And I will explain this in a slight more detail in the following. So the two game plans are slightly different, but in both cases, it's about computing anomalies, die-free anomalies on twisted string manifolds. Good. So what is the end point of this story? Well, for 10D non-SUSY strings, it's really easy to state the bottom line. These theories survive. So as far as we can tell, the three different Bordism groups associated to the three different theories vanish, or at least there could be potentially a single non-trivial generator in the case of the 0'B theory, which, recall, has a more complicated Green-Schwarz structure. But still, all the options, all the possible backgrounds that we looked at are anomaly-free. And there is an interplay between the anomaly cancellation of this type and other aspects of the theory.
Ivano, one quick question.
Yeah.
Even if, like, in that one, and you don't know if it's 0 or set 2, even if you don't find anomalies, in order to have like vanishing covariance class, one would need to find like some defect or some way to kill that set 2 in case it was the case, right?
Well, to do it, you would, if there were a non-vanishing Bordism class in this 0'B theory, one would need to evaluate the anomaly on this generator, right? Or a representative. If this anomaly does vanish, the theory is still anomaly-free. If it does not vanish, the theory is dead, unless there is an additional Green-Schwarz mechanism of a discrete type that comes into play. This is the kind of mechanism that was discussed in that paper, in the 2B paper by Ivano, Miguel, and Marcus and Jonathan, as well as an older paper by Marcus. So the point is, it's not, if the anomaly theory were to come out non-zero on this putative generator, the story would still not be settled.
No, I don't mean the anomaly, I mean the covariance class.
Yeah, it's
even if the anomaly is 0, right?
So I didn't hear that.
So even okay, so you come in the one in which you don't know if it's 0 or set 2. You said that there are no anomalies, but still, if like somehow you were able to do the computation and find out that it's set 2, you would need to kill that set 2 somehow, right?
I wouldn't say that necessarily. The D+1 dimensional Bordism that encodes anomalies is not of the same type of the lower dimensional Bordisms that encode topological symmetries that need to be killed or co-killed by defects and such. They're two different things. Like the lower dimensional Bordisms encode higher form topological symmetries, and I think that's what you're referring to.
Okay. Yes.
Yeah.
I should comment. It can't be killed, but it could still be co-killed, because you could still say that, oh,
Yes.
well, I didn't have the correct structure of my.
Absolutely. It could be that actually the structure that we need to impose is not this one, but it's more refined, and somehow the final Bordism group ends up to be 0 anyway. Yeah, definitely. Thanks for the comment. Okay, good. So this is the punchline for the top-down side of the story, but perhaps to give a bit more insight on why physically the anomalies cancel, we can look at a particular class of backgrounds, namely 11-dimensional manifolds, where one factor is a 3-sphere that carries the flux of the H field. And then there is a spin manifold of dimension 8. On these kinds of backgrounds, the anomaly simplifies a lot, because the anomalies of the chiral fields just die because of the sphere. And one is left with this integral of the x8 piece of the anomaly polynomial. So there's a link between the Difrid anomaly on this background and the anomaly polynomial itself. Turns out that there is a physical reason why this thing is always an integer. Namely, this x8 turns out to be the anomaly polynomial of a 5 brane that couples to the H field magnetically, right? And in these kinds of branes are usually well understood in the supersymmetric theories. And even in the non-SUSY orientifolds, they're just D5 branes. In the heterotic models, they ought to be NS5 branes. And this integral of the anomaly polynomial on a closed 8 manifold is just the index of some Dirac operator, right? It counts some chiral zero modes of the degrees of freedom on these branes, so it has to be an integer. So there is a physical understanding behind the anomaly cancellation, at least in these cases. And this can actually be leveraged some more, because you may recall that in the non-supersymmetric heterotic model, the NS5 brane is a really unwieldy object. We don't really know how it works in detail because we don't know the microscopic degrees of freedom, nor we have access to solid dualities to map it to something else that we understand. So what we did here, we used the cancellation of this particular index together with a very neat relation between the anomaly polynomials of the non-SUSY heterotic string and the ones of the SUSY heterotic strings to concoct a combination of chiral degrees of freedom that actually does reproduce this index. This is the result of a lot of algebra that was done primarily by Matilde, I should admit. But the end result was a really simple set of chiral degrees of freedom that may serve as a candidate for the chiral sector of the NS5 brane in the non-SUSY heterotic string. So this is a byproduct of the analysis of anomalies, I would say. So this is the top-down story. What about the bottom-up story, the 6D supergravity? Well, as I said, it's much more difficult to compute systematically all possible Bordism groups, unless perhaps in the future we find that they're actually all the same, could be. But meanwhile, we are stuck with computing on a case-by-case basis anomalies on simple backgrounds. And these backgrounds that we chose are mostly lens spaces. They are orbifold of spheres, now 7-dimensional, not 11-dimensional. And as I anticipated before, the anomaly, actually the semi-classical path integral itself for these theories contains these quadratic refinements because of the presence of self-dual fields. So when writing down the proper action or effective action for these self-dual fields, one is faced with the necessity to make sense of expressions like 1/2 x squared, or 1/2 of a sort of a Chern-Simons term, a abelian Chern-Simons term. And in the case of torsional classes, these things don't make sense naively. They have to be defined properly. And the proper way to define these things is exactly what quadratic refinements are. Now, in the case of spin manifolds, just normal spin manifolds, there is in fact a canonical way to define these things, which is based on a certain correspondence between characteristic classes and E7 bundles. And this is outlined in this super nice and clear paper here. But in the case of twisted string structures, there is no canonical choice. At least I don't know of any. And the same lack of canonical choices was pointed out also in a couple of previous papers on discrete Green-Schwarz mechanisms. So what we did was instead to, again, look at these simple backgrounds, lens spaces, and we just parameterized all the possible quadratic refinements. So the piece of the quadratic refinement that enters in the anomalies, is there someone asking a question?
Can I ask a quick question?
Yeah.
Oh, sorry. So, okay, sorry. There was a statement that if you have a spin structure in 7 dimensions, there's a canonical choice of quadratic refinement.
Yes.
I guess the loophole here that you're also looking at additional discrete bundles or
So the loophole, at least in my understanding, is that there is an additional obstruction, potential obstruction to this construction. So the construction of Tachikawa and collaborators is based on the fact that at least most of the time, the 7-dimensional spin boardism of BG vanishes for, let's say, Lie groups of a certain simple type. So you can just extend the d+1 bulk Y into a d+2 Z manifold, and then you can build your quadratic refinement as an integral over Z or of certain differential forms. So that's the canonical construction, right? And then you can turn this construction into a combination of eta invariants of E7 bundles. This
is the gauge group. The homogeneous of the gauge group, that's no longer true.
Well, first of all, that is definitely true. For instance, for discrete gauge groups, but even with the gauge groups that trivialize the spin boardism, the twisted string boardism may not be trivial, is what I'm saying. So that construction doesn't really take into account this further obstruction to extend Y into Z.
But okay.
It could be that the boardism actually vanishes and you can always do that. We just don't know.
Okay, thanks.
And in fact, if it is trivial, you can always do that, make that construction, and the resulting quadratic refinement will kill all anomalies, which is exactly what has to happen if the boardism is trivial, right? Everything fits together. The point is that until we know that the boardism for twisted string structure is in fact trivial, we cannot really make that leap. Meanwhile, we parameterized all possible gauge pieces of the quadratic refinement in terms of an integer m. So recall that the length spaces are ZP orbifolds of the 7th sphere, and this P appears here. Everything is mod B, essentially. And this B here is the B of the Bianchi identity. So that the B that multiplies, or not quite the same B, but almost, it multiplies the gauge piece of the characteristic class. What is the final result of this analysis? We can classify a bunch of families of supergravity theories and compute these anomalies. Turns out that some theories, some families of theories, can only be anomaly free if these M parameters are chosen very specifically for each background. And sometimes this, at least with the current information we have, would seem to be quite unlikely. Then again, it could happen that we find in the future that the boardism was trivial, so everything had to cancel anyway. But with the current information, what we can do is we can look at examples, and at least for me, the most interesting example physically is this family of with unbounded abelian charges found by Taylor and Turner. And we can look at anomalies in these theories. So first, I would like to mention just a quick intuitive argument for why this would be something bad. Why would these theories be in the swampland? Of course, there is the additional idea that we would like the landscape of inequivalent theories to be finite. But if we wanted to argue independently that these theories are sick, one way to do it perhaps could be to point out that they seem to be, at least they seem to be impossible to couple weakly in the electromagnetic sector, right? Because the effective gauge coupling that enters loops is not just the gauge coupling itself. It's multiplied by this parametrically large charge. And therefore, the magnetic weak gravity cutoff of the theory is actually bounded above by 1/q in Planck units. So it would seem that at least requiring a weak gauge coupling, these theories, these effective field theories would be obstructed somehow. The large Q limit would be obstructed. But this is a qualitative argument. What do anomalies tell us about this? And we can just happily compute these anomalies, because as it turns out, the only parameter that enters them is this very specific combination of charges, which goes to infinity in the large charge limit. So we have to essentially kill the anomaly for almost all betas if we want an infinite family to survive, right? So the anomaly takes a reasonably simple form, which depends on this quadratic refinement. And the Bianchi identity takes also a very simple form. And this P has to be a divisor of this thing, because the Bianchi identity has to be satisfied, right? The twistor string structure has to be satisfied. And at least two divisors are always there, just 3 and beta minus 1. Turns out that both require this M to be very carefully chosen for infinitely many theories. See, for P equals 3, so a Z3 orbifold of the sphere, if beta is odd, which is the case for like 3/4 of this series, then M has to be odd as well for infinitely many different backgrounds. Similarly, for this other lens space, it can be shown that this object, this quantity, is eventually never integer, unless, once again, this M is very carefully chosen between 0 and P minus 1. You have to pick 6 mod to P. I mean, it's a very specific requirement. And so, yeah, this is the main result, at least for this particular example. So there's another thing perhaps I can add, which is a comment on one question that was asked before, namely what happens in lower dimensions. Smooth compactifications of higher dimensional anomaly-free theories are anomaly-free automatically, but what about, for instance, orbifolds of the non-sociotheoretic string? A priori, there are no guarantees for anomaly cancellation, so we did look at 3 examples and we computed the anomaly under the SU2 subgroup here, just because it's the easiest piece. And turns out that there is a twisted string background that is allowed, and the anomaly cancellation requires the number of charged hypermultiplets to be a multiple of 8. This seems to be a non-trivial condition without supersymmetry, and it is non-trivially, I would say, satisfied in all examples. So once more, the bottom line is non-SUSY strings are safe. Other stuff seems to be perhaps not so safe unless the quadratic refinements are miraculously chosen, fine-tuned, or perhaps the Bordism turns out to be trivial. So this is what I wanted to say. Thank you.